and today is April 12th. And we want to talk about QCD. I have been postponing it, but it's a fundamental thing. You guys should have some idea of what QCD theory of strong interaction is. So what we want to talk about is strong interaction. Which is the SU3 gauge theory. It's all about gauge theory in the standard model. Now, it all started with the fact that quarks seems to be made. Protons and neutrons seem to be made. Proton is simply everything tells us that they are made out of quarks. The deep inelastic scattering. This is proton and neutron. Then we have mesons like pions. For example, pi plus. UD bar. And so on. K plus. US bar. And so on and so forth. So what we have observed in nature, either QQ bar systems or QQQ, no quarks have ever been seen in nature. No diquarks have ever been seen in nature. No Q bar. And so on and so forth. This is no. So imagine that you decide at some point that you want to build a gauge theory of strong interactions. I will give you additional reason why this happened, but imagine this is in 1967, Nambu. It is always Nambu, the father of modern particle physics. The idea of spontaneous symmetry breaking particle physics starts with Nambu. In 1967, he suggests gauging the so-called color. So in other words, people noticed that quarks carried color quantum numbers. And I was actually told, someone told me, I don't remember who it was, why I needed color. For example, delta plus plus particle, UUU, in order to have an antisymmetric wave function, you needed to antisymmetrize 3 colors. This is antisymmetric. So therefore, it is a singlet. In other words, what I mean is that quark transforms as U, Q under the color. There are 3 colors. So corresponds to that an SU3 symmetry. U dagger U is 1, and determinant U is 1. So if you wish, Q alpha goes into U alpha beta, Q beta. Q alpha, Q beta, Q gamma goes into U alpha, alpha prime, U beta, beta prime, U gamma, gamma prime, epsilon alpha, beta gamma, epsilon alpha, beta gamma, Q alpha prime, Q beta prime, Q gamma prime. Do you know what this is? It's a familiar object.
It's a determinant.
The determinant of U. That you can easily check. And that's one, what we assume. So this is invariant. So color, if there are three colors and corresponding gaseous symmetry, it would work beautifully. Now you've seen this almost in every example. You computed a W decay. When W decays, for example, into U d bar, W plus, U bar sum over color, and you get the correct result. You've checked yourselves, and so on and so on. There has been plethora of processes, cross sections, productions, decay rates. It's highly convincing. So Nambu got an idea that maybe we should gauge this color symmetry, and therefore we will have the messengers of force. So you see, because what is happening, the quarks, these quarks inside the hadrons, for example, what we are told that they are confined to be inside. It's like a shopping bag that is full of objects. You know, it's like you running with a shopping bag, but it's so tightly closed that the objects cannot leave the shopping bag. Okay, this is apparently the world in which you and I live. Quarks confined in hadrons. And mesons. Who is confining them? The gauge bosons. They do the job. They confine. And this is why people decided to call them gluons with this play of words. Give a Greek ending to an English word and you get a gluon. So I got gauge bosons. How many do I have in SU3?
8.
8. 8 gluons. That's the idea of it's all here. The fundamental thing is here. Now I'm going to have a question for you. From what I told you, you know, when we build the theories of nature, like the way we build a standard model, what did you and I do? Well, you and I are Newton or Einstein or whoever. It's always formulating in the minimal context. It's not only the principle as people stress you. If you don't write the minimal Lagrangian the way Hilbert writes and Einstein writes his equations, you wouldn't have any predictions. So if I have 3 quarks, the minimal gauge group that corresponds to 3 quarks is SO3 is minimal, not SU3. Why not SO3? We go back. You and I want to account for the world in which we live, in which we said, where is it? We see these objects, this we see. And we see continuously. This is the only thing that we see. But we don't see this. No. You see, Q is the object. When I write Q, let me write it in red. It's Q red, Q yellow, Q blue. What will happen in SO3? If you have a, so in other words, Q is a vector of this symmetry, a fundamental representation, whether it's SO3 or SU3, it's always a fundamental representation. This is my fundamental representation. We call it vector in SO3, but okay, it's just a name. Well, remember, if you have a vector V, that V times V is invariant. It's equivalent to saying that I can write V as a column, that V transpose V is invariant, where V is V1, V2, V3. In other words, if Q is a vector of SO3, then QQ is invariant. It will be a color invariant object, but the only objects we are seeing in nature are color invariant objects. I didn't say it in those terms, but that's what turns out. I don't see QQ. That means QQ is not color invariant. So maybe I didn't say it properly. I was driving you there, that maybe cheated a little bit, just to emphasize the point. What we see are only color. We see white objects. So while in SU3, there are only two ways of making white objects. White is color invariant. What I mean is SU3 invariant. There are only two ways of making that, as you know, Q bar Q, which goes into Q bar U dagger UQ, which is Q bar Q. That's one invariant. And the other invariant is Q, Q, Q with an epsilon symbol, which I said above. These are the invariants. Otherwise, you need many more quotes. So SU3 is the minimal gauge group. Minimal strong force. Okay, that's obvious. Minimal gauge group that can confine. So we have to learn SU3, but it's fun. It's some other little group to learn, okay? If it was SO3, there would be nothing to learn. We will have just SU2 symmetry as we do for weak interaction. So what I mean, I can write U, and as you know, but let me remind you, I write U. How do I write U? As e to the I h. If U is unitary, H is Hermitian. You agree? This is equivalent. U dagger is 1. But determinant U is 1, so trace of H is 0. Well, you know this. Any so in other words, I can write H as theta A. Let's use alpha, T alpha. We used to use alpha is 1 to 8. And these are the generators of SU3. T alpha, T beta satisfies some commutation relations. I don't know F. I don't want to learn it. How do I build SU3? Remember what I kept telling you? All you need to know is SU2. If you know SU2, you know group theory basically for almost everything in particle physics, almost. So a great deal. SU3, actually SUN is just Pauli matrices plus Cartan. What I mean, in SU2, just remind us, remember SU2 is the subgroup of SU3. So how do I build SU2? T1 is sigma 1 over 2. T2 is sigma 2 over 2. These are the off-diagonal one. And then there is Cartan. There is just one such generator because it's traceless. If it was not traceless, there would be two of them. There would be unity. But this way I have one, and let me specify it just to remind you because it's traceless. So this is in SU2. A little digression. That's all you need. I hope I'm boring you. So in SU3, I'll start with T1, which will be almost sigma 1. I'll put it because SU2, I've decided. So the SU2 subgroup first two components. Then the rest follows. So T2 is 1/2 0 minus I 0, and so on. Since I want to close SU3, I have to put the first member of Cartan. This is in Cartan. And of course, I'll choose it the way I did above. I need to make sure that the first three guys do SU2. That's my convention with you guys. Everybody else chooses it, okay? These matrices are called Gell-Mann. It's funny how we physicists, because we don't know usually a lot of mathematics, so we attribute the mathematical part to a physicist. So how would I choose T4? Well, Pauli matrices work, so I keep putting Pauli matrices. I can put it here. And then, of course, T5. And T6. I'm boring you, right? You're thinking, why don't I go and take some coffee or something? Why do I have to listen to this? And so T7, I won't write. You will write. I'm almost done. I have to finish the Cartan. That was the first part. What has remained? I have to finish with Cartan. T8. It must be orthogonal to this guy I call T3. So it must be like this. 1, 1. And here, well, it's traceless. And then there is some normalization factor. Remember that in SU2, we have a normalization factor, trace Ti Tj is 1/2 delta Ij for a fundamental representation for a doublet. This reproduces, this is equivalent with Ti Tj epsilon Ijk. Since SU2 is embedded in SU3, we must normalize. So any SUN fundamental trace T alpha, T beta is 1/2 delta alpha beta, any SUN, in particular SU3. on a fundamental representation. So I have the normalization. So who can tell me what n is? 1 over square root of 12. Am I right? To give me a half. 6, I think it's true. Check it, please. That's almost all you need to know about SU3. There are two interesting representations. One is a fundamental. This was a fundamental. I gave you Pauli matrices. There is a very interesting representation that we call adjoint. There was a vector in SU3. Remember, we call it sigma, and we decided to write like this. The adjoint. This one is surely perfectly well defined. How do I get adjoint? Well, I take fundamental times fundamental bar, which is 9. So it's 8 plus 1. Why plate plus 1? Because trace sigma goes into trace sigma, so that we can take trace sigma 0. So there are only 8 components. I separate the trace. Also, sigma is sigma dagger, remember? This is invariant under above. So when we need to talk about it, we'll talk about the adjoint, but you've learned it in SU2, so this is, I don't know how much I want to say really about the group theory. I pause to see if you want to ask me something, but I presume you know it. Okay. I think I'm happy with what I just told you about SU3. But look what my task is. There is a very, now comes very beautiful, interesting physics, okay? This is important. The rest of this lecture should be very useful if I manage to capture the essence. How do I know that there are quarks? I just told you that I've never seen a quark. I told you there are no quarks, but then I tell you that there are quarks. So you told me the other day. How do I know that there are quarks? Someone help me.
By scattering.
Sorry?
By scattering.
Right. Which scattering?
Deep inelastic.
Deep inelastic scattering. There is something which is called deep inelastic. Well, the name tells you it's deep inelastic. You can imagine all kinds of deep inelastic scattering. The prototype scattering in the late 60s that made its great discoveries, electron on proton scattering. So you have an electron coming in, emitting the photon, comes here a proton with 3 quarks, and what comes out, there is exchange momentum Q is arbitrary. Q squared is much bigger than proton mass squared. This is called deep inelastic. Deep inelastic scattering. You see, we are going to huge energy. This is a great microscope, right? Because large Q corresponds to small distance, much smaller than MP to the -1. So what we are probing, we are looking at the proton. And by this kind of scattering, we are looking here. We are looking in small region, okay? This is R, roughly 1 over Q. And therefore I can see what the gas is made of. And what happened is, what they've seen, the proton behaves as if quarks are almost free. Almost is very important. Not really. If they were really free, then there wouldn't be any gluons between them. There would be no messengers of the force. But it's very interesting. They're almost free, as long as, once again, as Q is much bigger than MP. The bigger Q, the more free. Okay? The bigger Q, the more free. It's called asymptotic freedom, by the way, this fact. And we say in the ultraviolet, at high energies, you get asymptotic freedom. So what we have to do is the following. We claim that we have a gauge theory, which is bizarre. At high energies, it basically doesn't couple at all. The gauge coupling should go to zero, basically. But if I go to low energies, I should find out. You see, I'm now learning that the opposite is true. When I go to very, very low energy, the binding is so strong that I can't even use the language of quarks. There are no quarks at low energies. There are only protons and pions. What I'm learning is that the strength of the interaction, the coupling constant, what I'm saying here, that the coupling constant is not constant. Presumably constant in time, although some people would like to challenge that too. There are people who says, oh, maybe even that, who knows? One day we'll see that it's not a constant, but it looks very constant in time. But it's not constant, it varies with energy. Alpha strong, surely, and that may be true for other constant, which is G strong square over 4 pi, is a function of Q or energy. What I mean by the G strong is that the definition of G strong is in the covariant derivative. Remember, it's all in the covariant derivative. D mu is d mu. When I tell you that there is a theory, all I have to write down for you is a covariant derivative. And the covariant derivative is minus I, G strong, T alpha, I call them, A mu alpha. Alpha is 1 to 8. This is what I mean by this is the strong force coupling. Now let me put the strong in brackets, because actually I'm telling you that the force is not strong. It's neither strong or weak. Apparently, if I go to very low energies, so at low energies, for Q, which gets to be less than M, alpha strong must be bigger than 1. For Q, much bigger than M proton mass, alpha strong must go to 0. This must be true. And you can imagine this was what was holding the progress until the beginning of the 70s, when it was noticed by Politzer, Gross and Wilczek, very interesting. Politzer was a graduate student working independently. Wilczek was a graduate student of Gross. So these were two young men who participate, who will get Nobel Prize for their work, have discovered that this is actually true. Now, what it really means, what happened? What do you see?
The cursor.
You see my iPad?
Yes, but
Okay.
the,
Sorry, I
the
thought
pen is like,
something went wrong. Okay, sorry. Good. Now, what you had to do is sort of, you know, to step back. So let's step back for a second. And let's think a little bit about QED. If I had to understand, if this is true, the same should be true in QED. And what it means, what do I have to compute? I have to compute the behavior of the gauge coupling constant with energy. Now, how do I do that? Well, I compute the loops. So let's do it. We always do, you know, the first things first. So we do one loop. So what are the loops that renormalize the gauge coupling? There is this, right? This you've learned. Am I right? You've learned this?
Yes.
This is called Z1. This is called Z2. What else is there? There is this diagram, right? So I take some fermion, for example, this can be the electron. This, of course, is the photon, 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 photon. Notice this interesting thing, any fermion, charged fermion is there. And reminding you of two important things, actually, these two cancel each other. This is called Z3, this particular loop. This is 0. Z1 plus Z2 is 0. This is very important. You probably paid attention. And we have this extraordinary thing in nature. The charges are quantized. We have a miracle in nature. For example, Q of the electron plus Q of the proton is less than about 10 to the minus 40. That's an extraordinary thing. This is equivalent to the fact that the charge of the electron is 3 times charge of the down core to a precision of 10 to the minus 40. Now that, of course, must be preserved by loops. Now Z1 and Z2 would not preserve that because they depend on the 3 times on the particle in question. Whereas this one, notice, is proportional. The beauty of these 3 is proportional to the original charge. So I can write that E, the coupling constant, is E0 plus E0 cube. This was 3 level. This is coming from Z3. And this is very easily sees is logarithmically divergent. Logarithm lambda. On dimensional grounds, this must be Q here. So this is actually a function of Q. Notice E of Q1 is E0 plus E0 cube logarithm lambda over Q1. E of Q2 is E0 plus E0 cube logarithm lambda over Q2. So E of Q2 minus E of Q1 is E0 cube, but then I can call E cube to this precision. I'm doing a perturbation theory. So here I can substitute E equally 0. That's the next order. So what do I get? Logarithm Q1 over Q2. This is what I was saying, that coupling constants. This is a clear momentum and or energy dependence. Notice that we get it because of the logarithmic divergence. There are people who say, you know, there were people, I never understood that from Dirac onwards. Dirac was troubled by the logarithmic divergence. He didn't like the fact that when lambda goes to infinity, this diverges. It drove him crazy. It's hard to understand. Now, Dirac is a genius, so what can I say? I don't understand what bugged him. I remember I was your age, doing PhD in New York when he gave a very interesting talk, which I thought, me and my friends, we thought it was crazy. We didn't understand at all what he was saying. It was not easy to understand there. He was saying that the entropy of the universe is too large, that there are too many particles in the universe, that was troubled him. Today, this is known as the horizon problem. This led to the famous inflation, okay? He anticipated that. We, of course, didn't understand. But we felt like asking him, why in the world was this bugging him? The fact that there is this logarithm divergence is the source of modern particle physics. It's the most beautiful thing in particle physics. Because of that, there is this energy dependence. And because of the energy dependence, it is possible that at high energies, you get a small coupling at low energy, big coupling, or vice versa, whatever it is, okay? It's here. It's just a dimensional argument. It's all here. By the way, we say that coupling constants, so alpha is a function of Q. We say that alpha runs, we say. It's not a good expression. It's really crawling that it does, you know, like a baby. It's logarithmically dependent. And you wouldn't notice this. You have to start building big machines to notice that. That's another reason why it took time. Because you got to make a huge change in your energy in order to see a logarithmic effect. It turns out that in QED, alpha grows with energy. I should have put some coefficient here. This is not, sorry, there was some coefficient C. And then the sign of C tells you it grows with Q. So the bigger the energy, the bigger the coupling constant. So in other words, at small distances, coupling is bigger. This is called charge screening, right? You must know this. You talked about this in your courses, in your field theory course?
No.
Right? If I have a same positive, negative charge sitting here, of course, quantum mechanically, what I see, there will be clouds of charges around it. So when I'm far, I see less charge. It fits. Now, the I mean, you know this, so was very brief. What I want to do now, you have to take my word for it. This is a hard calculation. This is usually the third semester of field theory. If you go and do PhD at CISA, they do it. They also do it in many American schools. People compute this dependence for energy. Now a graduate student does what was a Nobel Prize some years ago. And I'll give you the formula. We write like this. So the running of coupling constants in general, alpha gauge coupling. Doesn't matter what group we take. It has usually a name, renormalization group. It's historic, so let me not. Goes like this, 1 over alpha. I'll write energy, sometimes I write Q, is 1 over alpha V1 plus B over 2 pi. This is the same formula I wrote before, logarithm, but this is now generalized to be correct. The coefficient computed. The dependence is logarithmic, as I told you. You see, the loops that you have to compute are along this one. These are the longs that you have the cube, but in general, in Young-Mill theory, there are these diagrams. But there are also other diagrams, right? The gauge bosons interact with themselves, remember? In Young-Mills. And so on and so forth. And in general, you include this because Z1 may not be equal to Z2. You have to include all kinds of diagrams. It's a lot of work. And I have to give you B. You have to take my word for that. This is very important. B is 11/3 T gauge boson. This is contribution from gauge boson minus 1/3, minus 2/3 to fermion minus 1/3 T scalar. Coming from gauge bosons, from the name it's clear, from the fermions in the loop, and from the scalars in the loop. There could be scalars. In the standard model, there is a Higgs doublet, okay? I'm writing a generic formula. And T of any of these T, delta AB, is trace TATB. Notice an incredible thing, that the gauge bosons have opposite behavior from the fermions. Forget the scalars for the moment. Their impact is actually smaller. Notice two fundamental things. The gauge bosons have dominant effect. They dominate. And they have opposite effect. They anti-screen. And that's because of their, I don't have a nice simple explanation for that. That's because of their non-trivial interactions with each other, which is of course not in the case of the photon. So you cannot think of this trivial picture that I drew with an electron, with the clouds of the electron positron. There it is extraordinary complicated stuff of gauge bosons floating around. Opposite effect, no screening, anti-screening. So you see, because of gauge bosons in the Yang-Mills theory, B is positive. So in a Yang-Mills theory, in general, B can be positive. And we'll find out that in QCD it is positive. It is possible. Why is it possible? Because this guy dominates. But if B is positive, then 1 over alpha grows. So alpha goes down with energy. I get asymptotic freedom. So in a Yang-Mills theory, asymptotic freedom is, this was a great discovery. Asymptotic freedom is natural. Now notice what I'm doing here. There is a little cheat. Because you could tell me, oh, you've just proven confinement. Take the energy to zero, you'll get the coupling to be infinite. No, this is not true. I'm doing a perturbative calculation. So this is a perturbative result. This is one loop. Eventually, when the coupling gets strong, the thing breaks down. And this is the reason why there is no proof of confinement yet today. There is no analytic proof. In other words, what I'm saying here, when alpha goes to infinity, alpha QCD, when energy goes to infinity, alpha QCD goes to zero. When energy goes to zero, alpha QCD should go to infinity. This is proven. Let's just write down. This was never proven. There is no analytic proof. People are actually doing ugly computer calculations on the lattice, so-called Monte Carlo simulations, whatever. There are strong indications that this is true. As the people build better and better compute, that everything indicates that this is true and it agrees with nature, but there is no proof, really. In other words, we don't have really the analytic proof of what the vacuum of the QCD theory is. When we study theories of nature, when you study theories of nature, one thing is you need a Lagrangian to describe the theory. Oh, it's not writing anymore. Do you hear me?
Yes, we can hear you.
But it's not writing, notice.
Yes.
So what do I do? I forgot. What do I do here? Now, why does it happen? Let me just see if I go coming back. Yeah. You need a Lagrangian. You need a ground state. You need a vacuum. You know, you have to know the behavior of the theory. You can appreciate how hard it is. Very often people say that they will work out something like a string theory or whatnot. QCD, so naive, simple Lagrangian. I mean, I should have written it just to give you an idea. What is the Lagrangian of QCD? Let me just write it. I'm writing the quark when the quark have masses. It's as simple as this. You can appreciate how hard this is to solve any theory. And this is why we only do perturbation theory, because we simply don't know where G mu nu alpha is d mu a nu alpha minus d nu a mu alpha. You knew this plus G strong, F alpha beta gamma, a mu beta, a nu gamma. And once again, d mu is d mu minus IGS, T alpha, a mu alpha. That's it. I will pretend in whatever little time we have, you and I have to pretend that actually QCD does confine. There are strong indications, as I'm saying. Okay, no proof. The confinement, the strong part, is done on so-called lattice. Is a computer, Monte Carlo simulations. Lattice, you pretend that the space is quantized. Instead of working in a continuum with some small distance a, you do these computations and then you try to take a smaller and smaller. So confinement at low energies, this is called infrared slavery. Goes hand in hand beautifully with asymptotic freedom at high energy. Any questions? I want to play with some group theory, but I want us to take a break because there will be a little non-trivial part that I'm going to be checking on your group theory. And we'll try to figure out how to compute these T's. But this is a great moment to pause. So if you don't have any questions, let me see, what time is it? It's 11:56. Nothing urgent here, right? So if you don't ask me, let's meet at 12:05 so that the number is round. Okay.
Professor, may I ask a question?
Let me just 1 second. Yes, please.
Yeah, is there any symmetry which can be broken in QCD Lagrangian? Just out of curiosity.
Sorry.
Is there any symmetry which can be broken in QCD Lagrangian?
I'm not sure what. I'm sorry. Try me more.
Like, can we find any broken symmetry in QCD?
Is you're asking is SU3 symmetry broken or not?
Sorry. Yes, I mean.
So I'm I'm glad you're asking me. I should have said that. I should have said that. So we said the QCD is SU3. I should have said unbroken gauge symmetry. Again, we don't have a rigorous proof of that, but just like the confinement, we have strong indications that gluons are massless. You know, it's not like the case of you can think, or in the case of QED. In the case of QED, you can actually, masslessness of the photon is the long range force of electromagnetism, but the strong force is short range. Quarks are confined. It's like you can think, it's like this. Let's give an analogy. Let's take a meson. For example, a pion. So I have a quark. I have an anti-quark, say Q bar, and the quark. And here, you know, what is happening somehow, the imagine it's like as if these gluons are creating some kind of, you know, string between these guys. There is something confining them, right? There is a force between them. So people like this. This was Nambu's kind of nice kind of string picture. That's how I started the whole thing about strings and superstring. It starts very innocently. Nambu gets the idea, and he actually develops a string Lagrangian, Nambu Goto, that there is a string of these gluons, because they are very different from the so you are trying to pull them out. So what's going to happen? How come you cannot pull them out, right? So you pull them out. So you start pulling out. What happens is that energetically, it costs less energy to break the strings than to separate them. The string will break, and you will have a quantum mechanically, that's of course possible. Now we get another QQ bar pair, which of course doesn't contribute to anything. It's neutral. This is which has never been proven, okay, but there are strong indications that this is true. And this fits nicely with the Young-Mills unbroken gauge series, in particular SU3. In other words, the potential as a function of R looks like this. This is apparently the picture in QCD, not 1 over R. Inside, when the distance is not very big, when the distance is short. You constantly have to push in force, and that costs you a tremendous amount of energy, so the string will break. That's the picture. And it's not the same proof. I cannot look at this force outside because the quarks are not outside of the proton. So I can't tell you that I've checked the masslessness of the photon. I can tell you with what precision I know that photon is massless. I look at the Coulomb force. I can't do that. Cannot quantify it as nicely for the gluons. But yes, as you said, it seems that this series is unbroken. Unlike the SU2 symmetry of the standard electroweak, SU3 is not broken. More questions? Okay, look, you and I will know how to use this formula. This is formula 1 and 2 and 3. I wrote them again. I will know how to use 1 if I know how to compute T. So in other words, it goes like this. So computing, this was a digression. Computing T. T fundamental, we said, is a half for the fundamental representation. In other words, for doublet in SU2, it's a half. For triplet in SU2, it's a half. What about T adjoint? How do I compute adjoint? Any suggestions? You see, when the fundamental transforms like this, let's write in the same line. When the fundamental transforms like this, adjoint transforms as U, AU there. How to prove the, I'm interesting, I want to do it for SUN gauge here. I don't want to do separately SU2, SU3. Tomorrow, maybe you will tell me you like SU5. Or maybe, I don't know, some bigger SU group. You're allowed to build models. SUN gauge group. Let's do that. We can go to SO groups also, but let's do SUN. So how would I prove something that for Zen, for the adjoint? Let me give you the result. T of fundamental is a half. I can prove that T of adjoint is equal to N in SUN. How would you prove it? When something depends on N, what did you used to do when you were little?
Contradiction.
Sorry?
A contradiction, I was saying.
Contradiction? What do you mean?
No, sorry.
No, you mean something else.
Yeah, I was just thinking, is this proportional to the identity when we calculate the trace?
No, but the adjoint has how many elements? N squared minus 1. Which is the number of generators, right? So it's not the... No, how would you do it when something depends on n? There's a well-defined procedure in mathematics. You used to do that when before you knew in high school. Huh?
Induction.
Induction. Let's do it by induction. So I checked for n equal 2, obviously. There is no n equal 1. By the way, when n is equal 1, I should have said here, where is the formula 1? In an abelian theory, of course, the T-gauge boson is 0. That was obvious, right? The photon doesn't have charge. It doesn't couple to itself. So the first is n equal 2. So what is the adjoint of SU2? Adjoint is a vector, right? Which is a triplet. So you actually know it. What is it's spin 1. We can call it spin 1 if you wish. Remember, the generators are all normalized the same way, so it's enough to take one of them. So how does T3 look for spin 1? Which is diagonal.
One, 0, minus 1 on the diagonal.
Right. So trace T3 square is 2. It fits, it checks, it's n. So let's assume that it's n. So induction means that now I assume it's n, and I go from n to n plus 1. Now, what is the adjoint? Adjoint is n times n bar. That's what we said. The non-singlet part. So this is adjoint in n. What is the adjoint in n plus 1 group? It's n plus 1 times n bar plus 1. This is n times n bar plus n bar plus 1. But this is an plus n bar plus 1. This is a fundamental, remember? This is anti-fundamental. And this is a singlet. This is trivial. You can forget about it. So what is T corresponding of IAN plus 1? It is T of AN. You see, now they are separate representations, okay? They live in completely separate spaces. So if I'm the trace, I'm in different irreducible representation. What is a T of n of fundamental? It's a half. That's how we normalize it. All SUN groups must be normalized to half because SU2 is a subgroup of SUN. And of course, anti-fundamental is the same. It's just done through the complex conjugate. It's a half, and the singlet is a 0. But I assume that T of n is n. This was the assumption. And I get n plus 1. Checks, QED. It's extremely powerful, okay? Many of these results that you can do with sophisticated group theory I don't like to do sophisticated group theory because I don't know. I try not to learn unless I have to. So if I can derive things, I think I can almost derive everything now. We are not going to stay together enough to check me on. If I give a course on grand unification, it gets a little harder, which I've just taught a course recently where you have large groups and large representations, and you have to do that. So you see what we are saying. So we can compute this in QCD. This is very important. I just found that T have adjoint T-gauge bosons, which I call TGB, is N in SUN. And once again, T fundamental is a half. TF bar is a half. Just to be sure here that the fundamental representation, well, it was clear. Here I assume that the fundamental is what I call N dimension. Okay, so let's do QCD. N is 3. Okay, I don't have to do it. So the fermions, what are the fermions in QCD? Oh, I should have said here, I'm very sorry. I was not very clear. I was not complete. I may have been clear, but I was not careful enough. Where is my formula? Here. In this formula, the fermions are chiral. What I mean by that, now it will be clear in the example. What are the fermions? So this is equal, so this will give me T-gauge bosons. Now I have to do fermions. I have left-handed up quark, right-handed up quark, left-handed down quark, left-handed out quark. These are my fundamental representation. What is T of UL?
This is just half.
This is just half. This is a fundamental representation, a fundamental representation, a fundamental representation, fundamental representation. So in other words, T of quarks is 4 times a half is 2. Of course, leptons have, so when I say fermions, I mean quarks. Leptons have no strong interactions, only quarks. That means that the coefficient B of QCD is 11/3 times 3 minus 2/3 times 2, correct? I just calculated, right? Correct? Right? Wrong. What did I forget? If I want to go to high energies, it's good that I work with one generation because everything is there, but I should not forget that there are 3 generations. When you did WDKs, you remember that there are 3 generations. The formula should say here number of generations. And what we have seen now with the advent of the LHC, that number of generation is 3. So B of QCD, this is very interesting, is actually 33 minus 4 times 3 is 12. over 3, which is 7. It's manifestly positive. When I go at the energies, for the energies above, say, the mass of the W, mass of the top quark, you see, I have a very nice, I'm going to LHC, B is positive, so the QCD coupling constant is going down. Let me give you the number. The QCD, which sometimes is called alpha strong or alpha 3 for SU3, at the scale of MW, it's about 1/10. It's not precisely 1/10, just to remember it. Whereas alpha weak, which is alpha 2 at MW, is 1/30. Just to show you the alpha electromagnetic, sometimes called alpha 1, but alpha 1 could be hypercharged, so let's just call it alpha electromagnetic. Well, I can say alpha 1 just in case, because it's U1, it's around 1/120, something like this. Maybe a little bigger, 130 even. So notice that the weak coupling, the ratio between weak coupling and electromagnetic is bigger than the strong over weak. There is nothing strong about strong interactions. This is a small number. You can do perturbation theory. So what people are finding out, that they actually did this perturbation. So the quarks behave as they are almost free. You can compute the QCD corrections to the in the deep inelastic scattering. And of course, you do that. Anything that you do at the LHC, you compute the corrections from QCD, and the agreement is better and better as we speak. It's becoming a really not high precision, but almost. By the way, I can't help it. This is not the standard model. I'm going to say a few words beyond the standard model. I don't want to start something new. I got a few more minutes, so I want to whet your imagination. I'm sure you guys have heard that people talk about grand unified theory. The idea of grand unification which is often called quark-lepton unification, weak and strong interactions unification, developed by Patti and Salam, actually at the ICTP in the early 70s, and Georgia and Gleshow, always Gleshow. There is also important work of Georgia and Queen and Weinberg about running. This all happened between 73 to 75, 75, extraordinary productive period. And the idea is that actually you unify the standard model gauge symmetry, which is SU3 cross SU2 cross U1. You actually unify in some grand unified cut, we say, gauge group, single gauge group, if possible. Well, Patti and Salam didn't have a single gauge group, but that you unify the strong and weak interaction. So, of course, you know, in the beginning, it sounded crazy. Would have sounded, how are you going to unify strong and weak interaction? Strongs are strong, but weak are weak. What is the idea behind? For example, that means that you want to unify SU2, these are non-abelian, and SU3 inside some gauge group G. Can you tell me what is the minimal gauge group that can unify SU2 and SU3? What is the minimal group? Before I draw it.
0 SU5.
Let's just, sorry, which?
SU5.
SU5. Obviously. What it means that you have a fundamental representation SU5, which is 5-dimensional. Now, how will the 5-dimensional representation look like? Well, it has 5 elements. There are 3 elements here. This would be SU3. And then 2 elements here. There will be SU2. Remember, SU3 and SU2 commute. They cannot live together. They have to be separate. So it has to be SU5 as the minimal one. I could write SU4, but where I'm going to put SU2? Okay, SU5. And it's called Georgia Iglesias. There is a beautiful, it's so good a theory that it has been ruled out. It's very hard to write theories which are wrong. Let alone write, that's a miracle. But to write a wrong theory, it's not easy. Remember what Pauli says, it's not even wrong, he objects when someone is speaking. Most of the work done today is not even wrong. SU5. So how could they meet? How could I have, SU5 means, what does it mean? That there is one gauge coupling. So how can I have one gauge coupling when there are 3? How is that possible?
I mean, is it something like at some energy scale?
Right, very good. You see, the standard model is broken down to U1 electromagnetic times SU3 color. Today, we decided that SU3 color does not have to be broken. There is absolutely no indication that there is any breaking of SU3, so we will pretend that it's unbroken at some scale that we call MW. But it means that there is a gut gauge group. It will be broken to the standard model scale at some new scale, which is often called M gut. Sometimes called MX. There will be new gauge boson, and there are unknown gauge bosons. This will be some new gauge bosons mass. Obviously, there is a bigger group with a mass MX. But the gauge couplings constants are not constants, they depend on energy. So this is the picture. There is alpha, there is energy. SU3 goes down. We will see that SU2 goes down too, so they will meet. Of course, the coefficients are different. This scale we will call M gut. A miracle should take place. By the way, 2 couplings meet. That's not a miracle. The miracle is that U1 should hit it. U1 is growing. It's not asymptotically free. Remember, U1 doesn't have the gauge piece, so it's growing. And it has to know to hit it right here. After running by a huge portion of time, you will see, or space, better to say. I don't know if there is time. Let me not start something. I want to outline the thing. 12:34, we have a few minutes. We had a break, so let's speak a little bit. Let's just look at SU2. I need to compute the B2 often. I computed BQCD, where was that? 7. This is often called B3 or B strong. B2 would be the B of the weak interaction. So what is the T gauge boson in SU2? It's 2, remember? It's N in SUN. We proved by induction. What are the fermions in SU2? Let's look at the fermions. So these are gauge bosons. Fermions. We have UDL, nu EL, and then UR, DR, ER. So what is the T of UDL? Let's call this Q. Let's call this lepton. What is T of Q? Who's going to help me? I don't want to make a mistake, so I need your help. This is a doublet?
Is it 1/2 times 2?
It's 1/2 for doublet times, what did you say?
No, I said times 2, but it's just
Times
works.
3. There are 3 colors.
Yes.
Red, yellow, blue. Thank you. What about T lepton? We are doing for 1 generation. Then we'll multiply by number of generations. T lepton is 1/2. What about the Higgs? There is also the scalar, which is Higgs. What is T of the famous doublet? What is it?
Half.
Half. Every representation has the same numbers. Doesn't matter whether it's a fermion or a scalar or whatever in the world. Even if the gauge bosons were a doublet of that gauge group, you will put 1/2. The formula says coefficient is separated. Okay. So what I have is that B of 2 is equal to 11/3 times 2 minus, so what do I have for the fermions? I have 1/2 times 2 times 2/3 for the fermions. This is fermions times number of generations minus 1/3 times 1/2. This is the Higgs. This is 22/3 minus, what is it? I don't like what I said. This is not 2, this is 4. Nobody corrects me. How did I get 2? Tell me, how did I get 2? 3 plus 1. It's not 2. It's 4/3 number of generations minus 1/6. The number is not so nice. I can write that some number is, okay. This is 22 minus 12, it's 10/3 minus 1/6. Why don't I write it? It's 19/6. It's a number. but it's of course different from 7. This is what I said, that B2 and B3 run different. So we can compute the scale. So remember what I'm saying. Let me show you how we do this. 1 over alpha 3 at some energy scale E. I start running at MW, say, I measured it there. I could start at LHC plus B3, which was 7 over 2 pi logarithm E over MW. For whatever energy much bigger than MW. I want to be able to run far. 1 over alpha 2 over E is 1 over alpha 2 of MW minus, what was it, 19 over 6. So this is 12 pi logarithm E over MW. I can stop in at, what time is it? I'm almost done. So what is the MGAT? There's the scale when alpha 3 of MGAT is equal to alpha 2 of MGAT by definition. This is what you told me before. That's the scale where they apparently unify. So then I can actually compute. I got 1 over alpha 3 at MW plus 7 over 2 pi logarithm MGAT over MW is equal to 1 over alpha 2 over MW plus 19 over 12 pi logarithm MGAT over MW. You see 1 over alpha 2 minus 1 over alpha 3 at MW. Can write like this. Is a number that I could write 7 times 6 is 42. 42 minus 19, 23. But I know these things on the left-hand side. This is the great work of George Quinn and Weinberg. This is measured. And it's roughly, remember, 1 over alpha 3, I told you. 1 over alpha 2, sorry, is 30. 1 over alpha 3. So what you get is 30 minus 10 roughly is 23 over 12 pi logarithm MGAT over MW. This is 20. Anyway, you get that MGAT, I hope I didn't, is about 10 to the 16 GeV. An extraordinary prediction. A bit sort of, from the point of view at this point, I don't want to go on. I should stop here. Tomorrow we'll see what I do tomorrow in the last official lecture. But I wet your mouse. This is how the idea of very high energy physics started, that led to all kinds of advancements. It's, in a sense, I'm being ambivalent. There is a tremendous beauty in this program. There is also something scary that you start talking about physics that you cannot probe directly for a century or 2 or 3. We are doing experiments at 10 to the 3 GeV, so we have to go 13 orders of magnitude. You can imagine how long it's going to take to be able to directly probe. I stop here. You can ask me why in the world would you even talk about grand unification in that case. I'll try to tell you tomorrow. so that you have a sense of the fundamental, promising, interesting, motivating lines of research beyond the standard model, which are still genuine physics. One is neutrino mass, and the other, of course, is the potential unification of couplings. There is something really beautiful in this that I'll tell you tomorrow. Questions? Okay. If not, I'll see you tomorrow.
Thank you.
Tomorrow we got to talk a little more about the exam, and I want to know if some people want to meet to go deeper. Okay. Bye now.
Thank you.
Ciao.